Welcome everyone to our July's Doctor Data Science. We have Stephen and Nora today.
Hello.
Yeah. Nora, can you next slide, please? So as always, we do Doctor Data Science every third Wednesday at 9 a.m. Pacific. So next will be August 19th. And we post the recording on YouTube at this playlist. I'm going to post that link in a chat in a while. Over to you, Stephen.
Thanks, Ninad. Hey, everybody. Good to see you here in the middle of summer and our Doctor Data Science session for July. Last time, if you were with us, we covered regularization, kind of an extension of a previous talk where we talked about variable selection methods, and we talked about regularization in regressions and other machine learning models, in particular Lasso and Ridge. I thought it was really informative, a topic where it's easy to get confused, and certainly clarified some stuff for me. And as usual, we had our little info gain session, talked about how to explore a new data set from the beginning. This week, for our info gain session, we're going to talk briefly about model testing strategies. People typically use sort of champion challenger, and we'll talk about some alternatives or variations on that. The bulk of our time today, it's going to be difficult not to make puns throughout, the bulk of our time will be spent discussing time in the form of time series, and our guest Nora Hussaini will be leading that discussion. You'll remember Nora was talking to us a few months ago about, what was that, Nora? Was it text analytics, I think? Is that right? Yes, it was natural language processing. That's right. That was a lot of fun. Okay, so let's do a quick info gain then. How do I test a new model without losing money, right? So, if you're going to put a new model into production to make product recommendations or decide on positioning of an ad or to reduce churn or whatever it might be, there's always a chance that your model will not do as well as the champion, in quotes. And therefore, you want to be a little careful about how long you run that for and how often you run it, because you may end up getting some more information, but not actually, but losing some money in the process. The standard way to test new models, and not just new models, also new creatives like new banners or new ads or new target campaigns. Generally, people use A/B testing or champion challenger. I always get a little fuzzy on the difference between those two. I think of them as really roughly the same thing. But the idea with A/B testing, right, is that you've got two creatives, say, and you put them both out there, you see which one wins, gather some statistics about the ROI, and then put the best one into production. The problem with that is that you've got, by definition, one that is less effective in production for some period of time for some subset of your target population. It's easy to do. You just have a very simple rule on the front end that says route some percentage of your test subjects or your test transactions through each creative or each model or each campaign. But again, you might be losing money while you figure that out. So there's another approach, which is pretty well known, but I think it deserves to be better known. That's kind of the theme of our Dr. Data Science sessions, of course, is things that we should know that are often common practice, but perhaps not as well known as they should be, is the notion of multi-armed bandits, related to, if you've got a bunch of slot machines in Vegas, which arm do you pull to maximize your profit? Spoiler alert, they're all the same and you will lose money. Anyway, so the idea with models, and again, this applies to creative. In fact, I think it typically does apply to creatives, but there's no reason why you can't use this idea with predictive models. And what you do is you route most of your transactions through your existing or through your best model. And then what you do is that you take a small remainder, a small fraction, and you route the remainder of your transactions or your target population through just a randomly selected model. And then you start gathering statistics about that. And then what you do is you iterate and you keep on routing most of the transactions through the best one. But at each point, you're gathering more information about which one is actually the best. And so then instead of having just a static percentage of your models or your creatives seeing each particular version, you are instead constantly adjusting how many based on the latest statistics that decide which one is best. And so it's provably true under certain conditions that this will increase your ROI and reduce cost. And there are variations on this method that are more complicated versions of multi-armed bandit, but they're all the same basic idea, which is to gather statistics as you go along and adjust your strategy. So nice, simple, neat method that I think is worth considering as an alternative to just simple static A/B testing. Okay, so now let's go to our featured topic, which is about time series. Time series has been very much on my mind lately. We've been leading a couple of projects here at TIBCO, one where we're looking at electrical signals from smart meters. I'll talk about that in a second. Also some work we're doing around COVID projections, some novel work. And I thought it would be good to take a step back and sort of talk a little bit about how forecasting, nearcasting, and so on is done with time series. And Nora has been thinking about this too. So Nora, tell us what you found.
Thanks, Stephen. So before we begin, I just wanted to clarify what exactly we mean when we think of a time series, right? So if you just Google for a time series, what comes up in Google Images is something that looks quite varied. I mean, you can see that all of these different lines don't really necessarily have a pattern. The only thing that they do have in common is the fact that there is some kind of numeric component set across a time index, okay? We'll get into that in a bit. So why would we do time series? Time series and forecasting is important because we can look to the future, but it also helps us understand a little bit better about what's happened in the past, right? It's very applicable to all kinds of industries. It's very well known in, econometric fields and such, the stock market analysis, like that big dip that I'm sure you all noticed in the previous slide. But it's also useful for things like utility providers, knowing how to load, based on the demand that people will have at different times of day. It's also useful for refineries and for knowing how to control the processes and such. It's very, very applicable. And I think, Stephen, you have a couple of examples to give of how we harness it.
I like that you highlight, I mean, you think time series and you really do think about forecasting and sort of trend lines going off into the future. But just like with any other data science exercise, it's often as much about sort of interpreting and understanding the past. Yeah, as I mentioned at the outset, we've done a couple of projects. You mentioned utility studies. That's sort of indicated by the first screenshot here, where we're looking at essentially outputs of smart meters. And we did a whole bunch of stuff, including forecasting. But what to me was most interesting, I really enjoyed this project actually, was doing essentially clustering of time series. So interpreting the time series as really a sort of vector of values and just feeding those into standard clustering methods. Also using some other encoding methods, which we're actually going to be discussing in some upcoming Dr. Data Science sessions. But then we were able to identify naturally occurring types of electricity usage, which would be useful for marketing purposes and also anomaly detection, right? If you fall into a certain type and then suddenly leave it, well, that's kind of interesting to know. So those are the types indicated by those charts that we plotted there in TIBCO Spotfire. Also, the data science team has been working really hard on a whole bunch of analysis around the spread of COVID. And, if we go to the COVID analysis hub on tibco.com, you'll see a lot of information there, which we're developing along with various healthcare and government organizations, as well as some applications we're developing that we're going to help people get back to work. One of the things we've been working on in the lab, so to speak, is how to do the smoothing of cases, right? You typically in your newspapers, you'll see like a 3-day or 7-day average. We've been looking at things like super smoothers and actually applying things like GLM to be able to predict whether trends are likely to go up or down, and seeing some interesting results out there. So watch this space. So yeah, some useful and interesting applications there.
So let's dive a little bit more into what makes a time series really special, right? I mentioned that there is an index of some kind of time component. It can be any kind of time component. It can be, it can go as granular down to seconds and nanoseconds, depending on the context. But you can even go into decades, and it's very specific to your domain. The other thing to note is that it can be regular. So for example, if we were thinking about, the weather forecast and the temperature reported daily in a certain city, That's something that we tend to look at regularly, right? But it could also be irregular index, like if an alarm goes off. We don't necessarily expect an alarm to go off all the time, so we'd want to know why it went off, right? The key here about time series is that the data points relate to one another. So it is, you are basing your prediction based on where the actual target was before. It's not independent, and that makes it a little bit trickier than other machine learning algorithms that people are probably more used to. Two important things to mention about time series is also that there's seasonal and trend elements. So the seasonal element has to do with, as the word suggests, some kind of seasonality. And again, it depends on the domain. So I've put in two examples here where we're looking at e-commerce spikes. We typically expect them to spike around the holiday season, or how everybody decides in January that this is the year they're going to go to the gym and they sign up for their New Year's resolution. So there can be a seasonal aspect to your time series that might be important, and also a trend. Sometimes you might be increasing or decreasing depending on the context. So, for example, if we were looking at air pollution, that could be going up currently. It could be linear, it could be exponential. The scale is not necessarily important. The most common model that we're going to talk about, the one that I'm going to spend the bulk of this talk on today, is the Arima model. And unfortunately, the Arima model does not work with neither the seasonal nor the trending component. And we'll see how we tackle that in a bit. So, question. Why would we just not use linear regression? If we just have data points that, are numeric and across some index, why would you think linear regression wouldn't work?
So you're saying, like, you've got a bunch of Y values and an X value, which is time. Why not just regress one against the other?
Exactly.
Right, okay.
The reason you wouldn't do it is, if you were paying attention, is I mentioned that the target is related to its previous values.
Right.
And that is a very fundamental assumption in linear regression, that everything is independent in itself. That doesn't mean
sort of self-referential thing in time series, that one value kind of depends on the preceding ones usually, right?
Correct. And that doesn't mean, though, that there isn't a regressive element, but we have to be careful because there is definitely a relationship between the variables. They are not independent, right?
Got it. Cool.
So Arima, let's break this down. This is the time series model. Most people would have heard, if you've thought of time series, if you thought of forecasting, this is the model you would have heard of. It's sometimes referred to as Box-Jenkins, the people who developed this model. And there are three main components to the Arima model. There's the AI component, which is the autoregressive component, the I, the integrated component, and the MA, the moving average. So the autoregressive part is where I was alluding to before, is that there is a regressive component, but it is regressing on itself, right? So the auto, meaning self in Greek, it's looking back at its own lags and using those as predictors. And we will come to this concept of partial autocorrelation in a few slides, but we use these visualizations to decide on how much of an autoregression we should do. Okay, that will become clear in a second. The integrated element is sometimes known as the differencing term. So that's typically referred to as a D in the Arima parameters. And as I mentioned before, we need to make a time series stationary. One of the ways to do this is by just using a differencing term, so that we can make sure that there is no variation in terms of the mean or the variance. And more on that in a second. Then we also have moving average. That has to do with lags of the forecast errors. And we will be using we can use autocorrelation to decide what kind of moving average order we would be taking. This is sometimes referred to as Q, and I will explain this in a little bit more detail. But basically, we put these three models, right? So we have this Arima component, we have a P, a D, and a Q parameter that we have to configure so that we can find the signal from the noise.
Okay, so let me just make sure I got this straight. So it's sort of like three models in one, in a way, or three sort of learning processes in one.
Yes.
You've got these parameters that control those that you have to figure out in some way.
Yep.
And then one of the methods you mentioned there is around autocorrelation, which I'm guessing means sort of like correlation of the time series with itself, right? Looking how points
Exactly.
Okay, cool. Okay, great.
That's exactly right. And just to be clear, you don't necessarily have all of these components. You might have stationary
Right.
data, so it might be 0, your D might be 0. You might not need the autoregressive component. You might not need the moving average component, but the 3 together can be put together to make a time series model. It depends on your data. So to start with the autoregressive component, this should be quite familiar if you are used to a regression, right? So this is like the y equals mx plus c, except here the y and the x are the same. So the only difference is we're looking one value back in time. So the phi here is just that coefficient, the m that I mentioned before, and the autoregressive part, again, reinforcing that it's looking back on itself. If we had a p that was just one order, we would only be looking back one step, right, for each value. So we would only be incorporating the x to the t minus 1, right? So one step back. Is that clear?
Got it.
Yeah, this is usually the most intuitive part to the model.
It's sort of like, I think yesterday you made the analogy of like, people joke sometimes about the best way to forecast the weather is yesterday's weather. Just say it's probably going to be the same as yesterday. That's true here in Northern California, at least. So this is a variant of that, right? It's saying it's not the same as yesterday, but it's some sort of multiple of yesterday.
Yeah, exactly. So then the integrated component, this is the part which might be important if your data is not stationary, right? So just to reiterate what stationary means, it means that there is mean and variance that is constant. So I've pulled up the slide and I have a question for you, which is, which one is stationary? Okay, from all of these views.
Only one of them.
Which is?
There is only one that's stationary. I see like
no.
B and D.
I was trying to trick you here. So yeah.
B and D, H looks like it might be going down a little bit.
H is going down
G
a little
looks
bit.
kind of, well, I don't know. I'm going to say B at least.
Yes, so B is definitely stationary. Just as you said, the mean and variance doesn't move too much. Yeah. There is some variation, but it is stationary. Yeah. Also, G is, it's funny you mentioned H is on a downward slope because that would have been the one that tripped me up. But the point here is just that your data doesn't always look, it might look stationary, you might perceive it to be stationary, but that might not actually be the case. There are some statistical tests. There's one called the Dickey-Fuller test that you could use to test if it's actually stationary or not. And there is a technique to make your time series stationary if it is not already stationary. So in this example, what the difference between the graph on A and B is that we are taking a lag of just 1 day. And the difference between that day is quite constant. So you could use the Arima model with this, with the data points on the B side. You can then just map it back to your A with some kind of transformation. So whatever transformation you use.
I see. So B is basically a new time series created by subtracting the consecutive elements of the time series in A.
Correct.
Okay.
And that
it's kind of like differentiating in a sense.
Exactly. It's like taking a derivative. Yeah. So you are, and you can go back as far as you think that's appropriate, right? So this is how it is similar to a derivative.
And your previous slide that says that this is really the I part of the Arima, right? This is the integrated part where you can say, do the differencing as part of building the model.
Yes, exactly.
Okay.
So
cool.
this is still I part if your model, so as in not to worry if it's not stationary, there are techniques to make it stationary.
Got it.
So now the moving average part, the part that's sometimes referred to as the Q, right? So it's focusing on the error terms. The mu here is the mean of the time series. The epsilon, sorry, or the error term here is the random residuals, the residual deviations between the model and the target variable, okay? So in other words, this term represents the difference between the exact answer and the approximately correct answer that the model gives us.
Yeah.
This is probably the least intuitive part of the Arima model because it is a little bit tricky when you're thinking about errors, but essentially this is an unobservable parameter, and what it's doing is it's nudging the model closer to the actual values, right? But they're incorporating some part of the error into the regressive term, into the forecast of xt, right? So if it was sorry, go ahead.
Yeah, go on.
So if
Well, I was just
if
going to
it's
say, it reminds me a little bit of like boosting methods or iterative methods, right? Where you train the model and then you see what the error is, and you sort of go back and adjust it. It's kind of that method. So it's how the thing that confused me when I first saw this is sort of like, how can you refer to the error of a model when you haven't built the error yet? But the idea, right, is that you're iterating and converging.
exactly, you're iterating and converging. So if your queue, just to reinforce as we did with the AR example, your queue here, if it was a one order, so if Q equaled one process and your mean was 0, it would look, your term at every data point would be equal to the epsilon with some epsilon previously, okay?
Just one quick note there, in case people, that P at the end of that equation, I just realized should be a Q, right? That's the number of errors that you're taking into account.
Oh, yes, apologies, my mistake.
No worries.
Right, so how do we decide on the P and the Q? This is actually very tricky. And it is quite domain specific, but I'm gonna give it a shot by showing you some graphs that we tend to look at. So the autocorrelation element, you picked up on this earlier, right? Where we're talking about how, because the target variable, the part that we're predicting, is very much dependent on itself in the past. So we want to see, is there some kind of correlation between itself and then the next, the predictive value to come? So if we were to look at, say, xt as before, which is the target at time now, and compare that to the time 1 lag ago, and then 2 lags ago, and then 3 lags ago, so that's all of these different bars in the autocorrelation chart, you might think that there is some kind of correlation of the target with all of the variables that that came before it, right? So you might think that you would want to incorporate all of those variables into that component, thinking that they're significant. But we also use the partial correlation, autocorrelation, to examine if actually the correlation is happening because of that interrelationship, or if it's just a matter of looking at, you know, a term ago. So the partial autocorrelation is essentially looking between the two steps as opposed to one step with all of the steps that came before it.
I see. Right. So the correlations sort of get handed down from one step to the next, and the partial autocorrelation kind of removes that inherited bit and says, well, what's really correlated with the current variable, current time?
Yes, and in this case, it's showing us that actually what's really correlated is only one variable behind, right? So in this case, our P would just be 1. So our autoregressive component would be 1. But this is really...
We just use one. In the regression, we just use one term in that case. Yeah.
Yes, exactly. So this is really quite a difficult concept. It does depend on domain knowledge, as I said before. There is some trial and error. You might have different values of P and D and Q. Generally speaking, the advice is to start really simple and to start with one order and see how that works, okay? Well, what has happened is, because it is quite difficult, there are a lot of packages that have come up that abstract this concept away. So you don't even need to configure the P, D, and Q, it will find it for you. Packages in R, like Fore-cast, and Python, there's a pyramid Arima package, can find these for you. And then within TIBCO's products, in Spotfire, you can forecast to the future using the Holt Winters forecast. It's in the drop down from the tools. And soon enough in Team Studio, we will have an auto Arima operator, so it would find all those values for you.
Do you know how they're doing that in Team Studio?
It's quite complicated. It involves this concept called IKK information criterion. So you try out different models and you see you're optimizing based on this return from the IKK information
So I'm guessing
criterion.
some sort of grid search of the parameters. And yeah, the AIC actually came up in Peter's session a couple of months ago. So everybody should be familiar with that out there.
Yes, exactly. So you're using AIC to find the optimal parameters, correct?
Cool, great.
So Facebook has released an open source library that has taken a kind of different approach that people have been going crazy for. Some people love it because one of my friends who's a data scientist, she calls it baby time series. It takes it apart quite easily. So what they've done is they have a decomposable time series model with the equation as you see it in front of you. And the GT component refers to the trend. So that was something I mentioned earlier, which is inherent to a lot of time series. The S component refers to the periodic changes. And they also have this holiday effect, which just be careful when you're installing, because their holiday effect library caused me some issues with the installation, but it's incorporated into their model as well. And so what I wanted to do was I wanted to show you in a Jupyter Notebook. So I'm going to stop sharing for a second to show you in a Jupyter Notebook how this actually looks like.
Okay. And my understanding is that Profit is really popular these days, but it's tempting to say, well, then why bother using Arima? And I think, well, we decided to include it here partly because it helps you to understand the structure of time series, just understanding how it works. And also, you know, they tend to focus on slightly different problems, and Facebook's makes some simplifying assumptions, I think.
Yes, definitely. So and you're going to see how simple it is to use. So, but then again, as always, whenever you abstract something away, you're losing something, right? So, okay, so this is the Profit Python API. In the example they have in their quick start, they use this page, this Wikipedia page for Peyton Manning. I'll just show you this page really quickly. So Peyton Manning is an NFL star. He played, if you look at his career, he was drafted to the NFL a while back, and he played for the Colts and the Broncos up to about 5 years ago, right? So what they've done is they have a data set where they have the log daily page views, and the idea is that it would be able to show things like the trend and the seasonality quite easily. So if you're familiar with the sklearn library, this will be very, very similar to other methods. You just do the .fit.predict. What you do is you import the fbprofit library, and as with all other data frames, you import your pandas, you read in a data frame. Your data frame must have a time index here. So the DS here is the daily, the date itself, and the Y here is the log of the daily views for that Wikipedia page. Mm-hmm. And all you have to do is instantiate a Profit object and fit it to your data frame. So that's literally all you have to do. So m equals profit.fit. The only tricky part that comes about in using the Profit library is that you have to tell it in advance how far into the future you want it to go. So they have this helper function called the make future data frame. In this case, we're looking in a years to the future, right? Mm-hmm. And I'm just checking that here with the tail here. The great thing about, so as I said, it's .fit.predict, and we just put our future data frame into our model, and what it gives you is the prediction of what your Y value would be. So that would be the log daily page views with a lower and an upper limit as well. And they have a really cool function here, the .plot. So you can actually see the forecast, and this is the blue is the forecast of Facebook. As you can see it towards the end, there's no more black dots. Those were the actual values. Mm-hmm. Seems to be doing a pretty good job, right? Yeah. Yeah. And you can also see the bands showing up there as well. And they also have this .plot components, which is really interesting because we can see the peak of his career, shall we say, or when he was still playing, I think for the Broncos around this time, there were a lot of hits to his website, right? We can also see, I'm not sure, Stephen, is Monday Night Football a thing? I think it is, right?
You're asking the wrong person.
Yeah, well, I'm assuming it is. So, because there is a spike here on the actual day. And then we can also see in terms of the year that the football season is when there are a lot of people interested in that actual page. So all we've had to do is fit the model, so fit, predict, and then just plot components, and we'll be able to see a lot about the model.
Nice, that makes it very straightforward.
Yeah. So let me just go back to the slides really quick. These are some references that I've used to put together the stuff that I'm mentioning here today. One of the links here is from Duke University's statistical forecasting course. I really want to recommend Eileen Nelson. If you just Google her, you'll find great talks by her. She's very good at time series. She also apparently worked with famous politicians on political polling and stuff, but she's really a very good teacher. So I would definitely rate looking for her if you want, if you want more guidance with this topic. And of course, the Facebook Profit Quick Start page.
Great. Thanks so much, Nora. That definitely cleared up a lot of stuff for me, and at least gave me a sort of high level sort of map of how to think about Arima. So that's really great. Hey, Nina, do you want to talk about our next session and any questions that came up?
Sure. Yeah. So as you say, our next session will be August 19th, and it's on a survey of effectiveness of methods for categorical encoding. We have one question, guys. So John asked, can this be used to compare multiple time series against each other? And if not, are you guys aware of any such analysis that does that?
Yeah, this is related to that. This question is related to that project I was mentioning where we're looking at the electrical systems, where we really had like a huge number of time series that we want to analyze. So I'm really glad this question came up. I mean, just to step back a little bit, there are just so many methods at dealing with time series. People tend to immediately think time series, oh, Arima. But, you know, just transforming time series and understanding their structure and dealing with many time series and transforming sequences of time series data, even without forecasting, is a whole set of subjects by itself. So maybe we'll cover those in future areas. I know we're running a little over time, but just a quick answer would be that there are methods of comparing time series together. One of them has the coolest name in data science that I know, dynamic time warping, which is a feature in TIBCO's Statistica product. You can also use clustering methods. As I mentioned on the outset, you can encode time series to sort of simplify their structure and use that to find out relationships. You know, John, maybe there's a whole topic there for us to cover in an upcoming Doctor Data Science session. So we'll look into that.
Perfect. Do we have like 1 minute for one more question?
Sure.
So yeah, this person asking is, at the beginning you have said regression is not that optimal for time series, but profit is also regression, but maybe a bit more advanced. With profit regression, problems are solved.
Nora, do you want to take a stab at that? I think you know,
Sounds
I think
more like
your
a
point,
comment.
Yeah, I think more your point was not so much that regression doesn't help, it's just that you have to use a sort of variant of it, this sort of auto-regression idea, which I think came out in the first part of that model discussion, right?
Yeah, I think what I was trying to highlight is that we tend to forget that linear regression is independent, right? That the variables, when we're putting them into a linear regression, are independent. And the time series analysis, the fundamental aspect of it is you're looking at your variable, yourself, basically. You're looking at yourself and how you were, you know, a day or two or three ago. So you have to be wary of the fact that there's definitely a relationship. There's definitely a correlation there. Yeah, I thought that was more of a comment though. So
yeah, no, I think but it is a good one, and it's useful to highlight that. A regression is absolutely part of Arima, but it's this sort of special form of it, and you do have to sort of do this stationarity exercise first. Yeah. Great, thanks again, Nora. That was really fantastic. We'll have to have you come back for a third time.
Oh, all right. Well, thank you so much, Stephen. Thanks for having me today.
You bet.
Yeah, thank you, everyone, and hope to see you all in our next session in August. Thank you, guys.
Bye-bye.
Bye-bye.
Bye.